How's it going, everyone? We're going to do a couple of things real fast today for physics. We're going to cover Newton's second law of rotation. We're going to relate it back to Newton's laws of motion and forces that we did before. And then I'm going to give you a couple of helpful hints for your homework tonight towards the end of the video. You can see the examples that we're going to be doing in your book. If you go to your book onto page 258, that's where we're starting. We're doing section 9.4, and we're going to cover most of what's going on here, and we'll do a couple of examples from the book, so you can follow along there. The first thing that I want to talk to you about is something called moment of inertia. When we were doing Newton's laws in linear kinematics, we had equations that looked like this. The net force acting on an object was equal to its mass times its acceleration. And the idea is that for rotational kinematics, we want to have a similar relationship so that we know, based on the net torque, what the object will be doing. So we know that torque is equal to the force crossed with the radius vector, and if the force and the radius vector are perpendicular to each other and we just want the magnitude of the torque, then we know that the torque is equal to the force times that moment arm. If we were to look at how this affects Newton's second law, we have force times mass times acceleration. If we wanted to maybe look at how this is related to the torque equation, we could add in the lever arm on both sides of this equation, and in that case we might have something like this. We might have force times R, the lever arm, moment arm, is equal to mass times the moment arm times the acceleration. And then we also know one other thing. We know that the linear acceleration of an object is equal to its angular acceleration times r. So if we also made that substitution, we'd have that the torque is equal to mass times r squared times the angular acceleration. And this is where we're going to be working today. Newton's law says that the net torque acting on an object is equal to its moment of inertia times the angular acceleration. And in this case, the moment of inertia is the analog to mass between linear and rotational kinematics, just like linear acceleration and angular acceleration are thought of being analogs or related to each other. And this equation, mass times r squared, is a good way to express the moment of inertia of a small point particle, but it's not always the same. The moment of inertia depends on how the mass is distributed about the rotational axis. So it depends on how the mass is distributed. If you've ever watched figure skating, or you've done roller skating and spun around in a circle, you've seen that when people stick their arms out, they start by spinning slowly, and when they bring their arms or their legs inward, they're redistributing their mass closer to their rotational axis, and they start to spin faster. And that has to do with the conservation of angular momentum, which is something we'll talk about later. But the fact that they spin faster is because they are reducing their moment of inertia. It becomes easier to rotate them as they bring more of their mass closer to the rotational axis. So if you go to page 259 in your book, you'll see that same argument presented. For today, we want to remember that the net torque is equal to the moment of inertia times the angular acceleration. We're going to do a couple of examples based on that. Also, if you look in the book, you will see right here, you'll see several moments of inertia that are listed for different geometric shapes. So a thin wall cylinder, a solid cylinder, a rod that's being rotated about its end instead of the center. Just lost my place, 1 second. And you have a sphere, and you have a plane and a board and that sort of thing. And you can see that each of the moments of inertia are different. The general expression for the moment of inertia depends on the mass, and it depends on some distance quantity. Here they're using r and L, that relates how far the mass is away from the axis of rotation. So for this rod rotated about its end, L is the length of the rod. And you can see that all of the moment of inertias are basically the same. Mass times a distance squared, which is what we predicted when we were looking at the relationship between Newton's laws just a second ago. The only difference between all of these different shapes that have their mass distributed differently around rotational axes is a coefficient, the coefficient of the moments of inertia. So a thin-walled hoop has a coefficient of 1. A solid cylindrical disc has a coefficient of 1/2. And that makes sense because for the thin-walled hoop, if both those shapes have the same amount of mass, the thin-walled hoop has most of its mass distributed at a distance of r away from the axis, whereas a solid cylindrical disc has mass distributed all the way between on the axis and out to r. So some of that mass isn't having to be rotated with the same moment arm, the same length. The same thing with the bar down here. If I rotate a bar about its center, a lot of that mass is inward, close to the axis of rotation, and so the coefficient is 1/12. If I rotate the bar around its end, more of the mass is farther away from the rotational axis, so it's going to be harder to rotate, so the coefficient is 1/3, resulting in a larger moment of inertia if all other things are kept the same. In your homework for tomorrow, you guys will need to refer back to this chart to know what moments of inertia to use for different shapes. You'll also notice an interesting relationship, which is that a second ago I told you that the moment of inertia of a point particle, meaning just a small sphere with all of its mass concentrated at a small point, was equal to its mass times r squared, where r would be the distance of that point particle away from the rotational axis. But you'll notice that's the same moment of inertia as the thin-walled hoop. And that's an interesting property because when we're rotating things, it doesn't matter if I'm rotating one lump of mass a distance r away from the rotational axis, or if I smear all of that mass into a little hoop that has a radius of r. As long as all the mass, no matter where it's positioned, is a distance r away from the rotational axis, it'll have a moment of inertia mr squared. So the hoop and the point actually have the same moment of inertia for that reason. There's a lot of interesting rules that help you determine the moments of inertia of more complicated things. And we'll go through those later. Right now, let's do a couple examples. So we'll get back here. Let's make a new layer here. All right. So like I was saying before, let's look at just points of mass. So we're going to have a rotational axis here, and we're going to spin around this rotational axis. If we were looking from the top down, it would be in a clockwise motion. And let's put a giant point mass here that has a mass m. And let's put another mass out here away from the rotational axis that also has a mass m. And the distance between those two, or the distance between the rotational axis and the mass that's sitting out away from it, is some distance r. If I wanted to calculate the moment of inertia for this system, then all I would need to do is sum the two moments together. The moment of inertia of the particle at the axis is equal to mass times its distance away from the rotational axis squared, which in this case is 0. The moment of inertia of the particle that is sitting a distance r away from the rotational axis is its mass times r squared. So in this case, because we're talking about point masses, the mass that's sitting on the rotational axis isn't really contributing anything to the moment of inertia. And the total moment of inertia is mr squared. Let's look at a different situation. Let's imagine that instead of rotating about one end like we did, we rotate about the center. And so each particle's distance from the rotational axis is now r over 2. And they still have a mass of m. To calculate the moment of inertia now, I have mass, the mass on the left, times its distance from the rotational axis, which is r over 2 squared, plus the mass on the right times its distance from the rotational axis, which is r over 2 squared. And when I combine these terms, I'm going to get that this is 1/2 mass times r squared. So in this case, it's easier for me to rotate both masses about the center instead of about one end. Because I have a coefficient of 1/2 here, that moment of inertia is going to be smaller. And that's the general idea behind calculating moments of inertia. If I want to calculate larger moments of inertia or more complicated moments of inertia like spheres and disks, I might be able to use some geometry, or I might need to use a little bit of calculus. And that's something that we'll do later. Right now we'll just use the moment of inertias from the book. Alright, so next let's do a problem that involves moment of inertia to see how this can be applied. You're going to need to click on the second video link to continue this lesson.